Have you ever really stopped to think about what happens when you run a program? You type out some code, you click run, and poof, it just works. It honestly feels like magic, but it's not. It's this incredible, totally hidden journey that every single line of your code takes, from a simple text file all the way to electrical pulses firing inside your processor. Today, we're going to pull back that curtain and follow the trail. So, you've got your code, right? Maybe it's in Python, C, or Java. It uses words, symbols, things we can actually read and understand. But here's the thing. Your computer's brain, the CPU, doesn't speak English. It doesn't speak C. It only speaks the raw language of electricity, on and off, ones and zeros. So how in the world do we bridge that massive gap? How does our text become an action for the machine? That's the big question we're digging into. We're going to follow this journey through 5 key stages. It's a real transformation. We'll start with your source code, the stuff you actually write. Then we meet the master translator, a tool called a compiler. After that, things get a little weird with something called assembly language. Then we see the final form, pure machine code. And finally, we get to the heart of it all, how the CPU actually executes those instructions and brings your program to life. Okay, so our first major leg of the journey is all about translation. We're talking about going from the world of human ideas, written out in plain text, to the world of the machine, which is just pure electricity. Let's see how it works. It all begins right here with what we call source code. As you can see, this little C program makes perfect sense to a human programmer, but to the CPU, this is absolute gibberish. It might as well be a foreign language from another planet. This is the great divide we need to cross. And this is the hero of our story, the compiler. Think of it as a brilliant, hyper-specialized translator. For a language like C, you might use a compiler called GCC or Clang. Its only job in life is to take our human-friendly source code and meticulously convert it into instructions the CPU can actually do something with. This is different from an interpreter, by the way, which kind of translates on the fly. A compiler does all the work up front. So the compiler's first big move is to translate our C code into this. This is assembly language. And what's so cool here is that you can still kind of read it. Assembly is a very low-level language that maps almost one-to-one with the CPU's own operations. Move literally means move this piece of data, and ret means return. See? We're getting one step closer to speaking the machine's native language. And here it is, the final step in the translation. That assembly code gets converted into pure machine code. These are the raw numbers. We're showing them in hexadecimal here to make them a bit easier on the eyes, that the CPU will actually execute. This is the true language of the processor. Our simple little return 0 command has officially become this precise sequence of bytes. Okay, so now we've got our machine code. We're ready to go. But wait, before the CPU can run it, that code needs a place to live inside the computer's memory. So for this next part, let's take a look at how a program carves out its own little home for itself to live and breathe in. So the moment your program starts, the operating system sets up this nice structured memory map for it. The text section, that's where our machine code, the instructions, get loaded. The data section holds variables that are set up from the start and stick around. And then you have these two dynamic living areas, the heap and the stack, which are constantly growing and shrinking while the program runs. Let's look a little closer at those two. Now, the stack and the heap are where all the action happens. The stack is super organized. It manages function calls and their local variables, and it usually grows downward in memory. The heap is a bit more of a Wild West. It's for memory you ask for manually, for things that need to stick around, and it grows upward. They actually grow towards each other, giving your program a flexible space to manage all its moving parts. All right, our machine code is loaded into its cozy spot in memory. It is time for the main event. We are now going deep inside the CPU to see how it takes those raw numbers and actually brings our code to life. You know, every single CPU, from the one in your phone to a giant supercomputer, lives by this one simple 3-step loop. First, it fetches an instruction from memory. Then it decodes that instruction to figure out what am I being asked to do. And finally, it executes that operation. This fetch, decode, execute cycle is the heartbeat of your computer, and it happens billions of times every single second.
So let's see this in action with our code. The CPU fetches those machine code bytes from memory. It decodes them, and its internal logic goes, I know what this is. This means move the value 0 into the EAX register. Now, what's a register? Just think of it like a tiny, super fast little scratch pad right on the CPU itself for doing quick math. Finally, the CPU executes the command, and boom, the number 0 is placed into that EAX register. That's it. That is the fundamental building block of all computing.
All right, let's zoom back out for a second and look at the full picture. Let's trace that entire incredible journey one more time, from a simple file on your computer to a program that's actually running. This table really gives us a fantastic bird's eye view of the whole thing. We start in the comfortable world of humans with source code. Then the compiler takes us on a two-step translation, first into that low-level assembly text, then into pure machine code. And finally, the hardware itself, the CPU, takes over and starts executing. It's a journey from human abstraction all the way down to physical reality. So if you walk away from this with anything, I want it to be these 4 key ideas. First, you write code for other humans to read. Second, the compiler is the magic translator that prepares it for the machine. Third, the operating system gives your program an organized home to live in. And finally, the CPU brings it all to life with that simple fetch, decode, execute cycle, over and over again at unbelievable speeds. And just think about this for a second. Every single piece of software you've ever used, from a tiny calculator app to a massive, world-class video game, is built on this exact same foundation. The only real difference is the scale. Instead of one instruction, it's millions or even billions of them, all following the exact same journey from text to execution. So next time you launch an app, just take a moment and appreciate that incredible high-speed dance that's happening right under the surface.